In this module, we will be looking at an algorithm for checking the emptiness of Bucci automata. Look at this Bucci automaton. Suppose I ask you this question: is the language of this NBA empty? So what do you think is the answer? So we need to look at parts in this automaton and see, is there an accepting run at all? So how do we do that? It turns out that for this automaton, the language is not empty because if you see the word A, B, B, A, B, 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 A, B, 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 A, B and so on, it has an accepting run. So starting from Q0, you go to Q1 and keep doing this cycle, and since this cycle contains this accepting state Q2, this would be an accepting run of this NBA. We don't care what the exact alphabets are in each transition, as long as there is a cycle of this automaton which is reachable from the initial state and it contains an accepting state, we are done. The language of it will not be empty, and this kind of a reachable cycle containing an accepting state will be an accepting run of the automaton. Let's look at another example. What about this automaton? It has two accepting states. Any accepting run has to have either Q2 or Q3 infinitely often. Look at this cycle. This cycle can be iterated infinitely often, giving rise to an accepting run on the word ABA, ABA, ABA and so on. Yet again, this is a cycle which is reachable from the initial state. There is another way of looking at it. Q2 is an accepting state that is reachable from Q0, and from Q2, if you explore the automaton, you will get back Q2. You can look at it as an accepting state which is reachable and it is part of a cycle. Okay? One more example. Is the language of the above automaton empty? Yes, because the only accepting state is Q0 and Q0 is not part of any cycle. Once you leave Q0, you cannot get back to Q0 again. Okay, so this NBA does not have an accepting run. You look at any infinite word, try to run the automaton on that word, you will never see Q0 infinitely often. So the language of this NBA is empty. One more example. What do you think of this automaton? It has two accepting states. Is the language of this automaton empty? No, because you see there is one run which can cycle through an accepting state. Moreover, this accepting state is reachable from Q0. So AB, AA will be accepted by this automaton. So we have seen some examples. To check if the language of an NBA is empty, we need to find a reachable cycle in the automaton that contains an accepting state. By reachable, we mean that some state in that cycle is reachable from Q0, and from there when you explore, you will get a cycle back to itself. How can this be translated? Do a preliminary depth first search to get all the reachable states in the Bushy automaton. Now once you do this, look at every accepting state, and from every accepting state do one more DFS to see if you can come back to itself. If you can indeed come back to itself, it means that the accepting state is part of a cycle. Moreover, the accepting state is reachable as well. So the first DFS will give us existence of cycles, but we also want to know if the cycle contains an accepting state. So to do that, we have to do these two DFS procedures. First, do a preliminary DFS to get all reachable states, and from every accepting state, do a secondary DFS to see if it can come back to itself. We will run the algorithm on the 4 examples, and then you will get a better idea. So we will be seeing what is called a nested DFS algorithm. It will be using the idea that we saw in the previous slide, and this algorithm was presented in this paper. So here is the algorithm. It contains two DFS procedures called DFS blue and DFS red. The DFS blue procedure is responsible for exploring all the reachable states of the Bushy automaton, and from every accepting state we call the secondary DFS called DFS red to check if you can reach the node S again when you start doing the DFS from S. Let us try to work it out step by step, and then we will understand. Okay, so we want to call procedure nested DFS on this example. What it does is it first calls DFS blue of S0. So here S0 is the initial state, which will be Q0. So you have to call the procedure DFS blue on Q0. You come here. What do you do? So procedure DFS blue on Q0, it first sets Q0 dot blue is true. So there are two bits, blue and red. For Q0, now the blue bit is set to true. That is what is depicted here. You have Q0 and its blue bit is set to true. Now, for all t in the post of Q0, that means for all transitions out of Q0, here there is only one transition, do this loop. T will be Q1. Check if Q1's blue bit is false. Yes, it is, because we have not seen Q1 yet, and initially all the bits are set to 0. So Q1.blue is false. So now you should call DFS blue of Q1. Okay, this is a recursive procedure. So now you will call DFS blue of Q1. So what we will do, Q1.blue will be true. So we are at this position now. We saw one transition of Q0, and now we are calling the DFS blue from Q1. The blue bit of Q1 is set to true, and now what it does, it looks at all transitions out of Q1. There are two transitions. Suppose it takes the transition to Q2 first. Q2's blue bit is still false, so it will call DFS blue of Q2 and set Q2's blue bit to true. Now do the same thing from Q2. For all positions out of Q2, check if the successor's blue bit is false. Yes, Q3's blue bit is false. Now you will be calling DFS blue of Q3 and setting its blue bit to be true. Now, what are the successors of Q3? There is only one successor, Q4, and its blue bit is false. So you will call DFS blue of Q4 and set Q4's blue bit to be true. And now what? Let us look at the successors of Q4. There is only one successor, which is Q1, but Q1's blue bit is already blue. I mean, in the sense Q1's blue bit is set to true, so this if condition will not be satisfied. And since there is only one successor for Q4, you will get out of the for loop in the procedure DFS blue of Q4. Now you will check if Q4 is an accepting state. No. So you come out of the DFS blue procedure of Q4. Since it was the procedure of Q3 which called it, you will go back to this point of DFS blue of Q3. Now you check if Q3 has any more successors. No. You come out of the for loop of DFS blue of Q3, and now you check if Q3 is an accepting state. No. So you come out of the DFS blue procedure of Q3 and get back to this point in the DFS blue procedure of Q2. There is only one successor of Q2, so you come out of the for loop of DFS blue Q2, check if Q2 is accepting. Yes. Then what you do is you set the seed to be Q2 and call another DFS procedure called DFS red on Q2. So what this does is so here this is what happens when you had seen Q4 to Q1. Yeah, now at this point of time you are here in DFS red of Q2. What it does is it first sets the red bit of Q2 to be true. And then it looks at all transitions out of Q2 and checks if the red bit is true or not. Q3's red bit is false, so you will call DFS red from Q3, set its bit to be true. Then you look at the successors. You will call the DFS red from Q4. Then you will look at the successors. You will call DFS red from Q1 because it is, its red bit is false. So now we are in the DFS red of Q1. What we will do now, we will look at all successors of Q1. There are two successors, Q2 and Q6. Suppose Q2 is seen first. So T will be Q2. Is Q2.red false? No. What is the other condition? Is Q2 equal to seed? Yes. If you remember, we called DFS red starting from Q2 and we had set the seed to be Q2. Yes, Q2 is the seed, so you report cycle. So essentially what this algorithm does is, first the blue DFS looks at reachable states, and then when it is in an accepting state, it starts a red DFS, and the red DFS checks if you can come back to red again. So here the red DFS chose Q2 first. It's also possible that the red DFS chooses Q6, Q5 first, and then it will look at the node Q2. In any case, it would have found out that seed is equal to Q2 and it would report a cycle. Let's run this on this example. So we call the blue DFS at Q0. We look at its successors, go to Q1 and set its blue bit to true. We then look at the successors of Q1. There are two successors. Suppose the DFS chooses this successor and calls the DFS blue of Q3. So the blue bit is set to true. Now it looks at all successors of Q3 and checks if the blue bit is false and calls the DFS blue on the successor. So here it will be Q4. Now Q4's blue bit is set to true. You look at the successors of Q4. There is only one successor and call the DFS from Q5. Q5, you see what are the successors. Now there is only one successor, but its blue bit is already set to true. So you come out of this loop in DFS blue of Q5. You check if Q5 is accepting. No. So what you will do is, you will leave this place and get back to the DFS blue of Q4. Now Q4's for loop will also be over. Q4 is also not an accepting state. So you will come back to the DFS blue procedure of Q3. Now Q3 has only one transition. So you will be done with the for loop of DFS blue of Q3 and then you check this. Yes, Q3 is accepting. So you set seed to be Q3 and start the red procedure from Q3. So Q3's red bit will become true. You look at all successors. Now you will call the red procedure from Q4 and then you will look at its successor Q5. Now all successors of Q5 are colored red and none of them is the seed. So you come out of this for loop and get to the red procedure of Q4. Similarly, all the successors of Q4 have been dealt with. So you leave the DFS red procedure of Q4 and come back to the DFS red procedure of Q3. There are no more successors left. So you get back here to the DFS blue procedure of Q3. Okay. And now the DFS blue procedure of Q3 gets terminated and you get back to the DFS blue procedure of Q1. I hope you understand this. So the DFS blue of Q3 had called this internal red and that is over now. And so you get back to the blue procedure of Q3, which is called from the blue procedure of Q1. Now you have to continue. You look at the other successors of Q1, which is Q2, set its blue bit to true. Look at successors of Q2. One successor is Q4, it's already explored. Its blue bit is already true. Now look at other successors of Q2, Q0, it's also explored. So the for loop of Q2's blue procedure ends. And since Q2 is accepting, you should call the red procedure from Q2. So its red bit is true. Now look at all successors. Look at Q4. Is it already red? Yes. So you don't have to redo the red procedure from Q4. This is very important. Since Q4's red bit is already true, one doesn't have to start the red procedure from Q4 again. Look at the other successor, make its red bit to true and call DFS read from there. Q1, make its read bit to true and call DFS read from there. One successor's read bit is already true. Now look at the other successor. Its read bit is true. Its read bit is true. So this if condition is false. However, the else condition will become true because Q2 will be the seed. And since Q2 is the seed, it means that starting from Q2, we have a way of coming back to Q2 again. And hence you will report a cycle. So one point to see in this example is that this part of the DFS was already done and the DFS read from Q2 made use of this information. So each procedure, DFS blue and DFS red, will visit a node only once. Let us look at the other two examples as well. So here, suppose we start the blue procedure from Q0, look at its successors. Q1 will be now explode in the blue DFS. Look at its successors. Suppose Q5 is explode first, its blue bit is set to true. Then Q3's blue bit is set to true. Then this transition is explode. Since Q1 is already true, the blue of Q1 is already true, the procedure at Q3 ends, and then you jump back to the procedure at Q5. There are no more successors left to be explored in Q5. So you get back to Q1, the blue procedure of Q1, and now you explore this transition, set its blue bit to be true, look at the successors of Q4, go to Q2, and then explore this transition. Since there are no more transitions left to be explored at Q2, you will end the blue procedure at Q2 and go to the blue procedure at Q4. No more transitions left. So you get back to the blue procedure in Q1. No more transitions left. So we get back to the blue procedure of Q0. And the for loop in the blue procedure of Q0 will end. And now this statement will be executed. Check if S is accepting. Yes, set the seed to be S and call DFS red. So we are starting the red DFS from here. As usual, since Q1's red bit is false, Q1 will be explored in the red DFS, then Q5, then Q3. Q1 is already red. So right now we are in the DFS red procedure of Q3. You look at the transitions out of Q3. Q1 is already red. So this part will not be satisfied. It is not the seed as well. The seed is Q0. So this part also will not be satisfied. And you will leave the DFS red of Q3, go back to DFS red of Q5. And Q5's successors have been explored. So you go to the DFS red procedure of Q1. Look at the successors of Q1. There is Q4 which is yet to be explored. And its red bit is false. So now its red bit will be true because you have called the DFS red from Q4, and then from there the DFS red of Q2 will be called. And look at the successors of Q2. Q1 is already red and it is neither the seed. So you end Q2's DFS red and go back to Q4. Nothing more left from Q4. You get back to Q1. Nothing left from Q1, and there are no more successors out of Q0. So you leave the for loop of Q naught as well and reach here, and the algorithm terminates. You will see that from Q naught, if you start the red DFS, you will not be able to see a Q naught in this part of the program. Okay, whenever you check all the transitions out of any state in this red DFS, you will never get a transition to Q naught. This means that there is no cycle that Q naught is part of, and hence the algorithm will not report a cycle containing an accepting state. Let's look at the last example. So we are at Q naught. Let's run through it. You will see Q1. Suppose the DFS chooses this transition, Q2, and then there is one transition out of Q2. Yes. Now since Q2 is an accepting state, it will start the red DFS from Q2. Yes. And it will look at all transitions out of Q2. So Q2 is one transition. I mean, there is a self loop. So Q2 belongs to post of Q2. Is Q2's red bit false? No. Come to the else part, but Q2 equals the seed. So you will report cycle. So in this case, the DFS had chosen this set of transitions and we could find this fast. However, it might be possible that DFS chooses this, and then it comes back to this, and then it sees this and this, after which you might see the cycle. I mean, I just want to let you know that the number of steps, in the sense, not the worst case behavior, the running time of the algorithm depends on the order of exploration. However, in the worst case, the complexity is what the complexity of a normal DFS would be, but it could be the case that the algorithm runs at different speeds on the same example if different orders of exploration are taken. We do not have a control over this because we cannot guess which order will lead us to the accepting state. Given a generic Bushy automaton, we cannot define any order. So we have to let the algorithm explore all possible orders and then wait to see if there is a cycle or not. So we have seen an algorithm for checking emptiness of Bushy automata. And why would this be useful? If you remember, we started with this question: does transition system satisfy the omega regular property? The omega regular property is defined using an omega regular expression, and the omega regular expression can be converted into an NBA. We saw this in the previous module. A transition system also can be converted into a Bushy automaton, and the question of whether the transition system satisfies the omega regular property is an inclusion problem, and this inclusion problem can be reduced to an emptiness checking problem. And since we have an algorithm for checking emptiness, we have filled the gap in this flowchart. So now let me recall the higher level view. So we have transition systems properties and we give them in new SMV, and new SMV somehow checks it for us. To understand the internal algorithms, what we will do is, in the next week, we will see a generalization of GF, X and GF into what is called the LTL logic. And similar to omega regular expressions, LTL logic formulas, they are called, can be converted to Bushy automata. And of course, the transition systems can be converted to Bushy automata as well. And then we will make use of this conversion into complement and checking emptiness. That will give us the answer to whether the LTL formula is true or the transition system. So that is why we had to go through this automata step. To solve the model checking problem for this logic, Bucci automata will turn out to be very useful. There is just one step left. Usually when LTL formulas are converted, they get converted to what are called generalized Bucci automata just for convenience. In the next module, we will see what this generalized Bucci automata are. It's a small generalization of Bucci automata. However, it does not add any expressive power in the sense that we can convert any generalized Bucci automaton to a Bucci automaton. It's just some kind of a syntactic sugar. We will see that in the next module.